So this second video in our little series on wave-particle duality looks at how X-rays are used in medical imaging to have a look at what's happening inside of our body. So in the previous video we looked at how X-rays are produced through the process of Bremsstrahlung. Here we're going to look at what medical specialists have to consider when they use X-rays for particular medical applications. So to start off with, here on the title page you can see an X-ray image taken by Wilhelm Röntgen in 1895. He was the guy who really invented X-rays, and that's an image of his wife's hand. Now we will come back to that a bit later on when we talk about X-ray exposure times. Now we already know that X-rays have much shorter wavelengths of visible light, like we're talking thousands to tens of thousands of times shorter, and therefore, according to Planck's law, they must carry significantly higher energies per photon. Now what this means is that whereas visible light can't pass through your body, X-rays can pass straight through and to the other side, and it's this property that allows us to use X-rays to see what's happening inside our body, to see our bones and to see our internal organs. Now, this short wavelength for X-ray light also means that we can't focus X-ray light with lenses. So unlike other sorts of imaging systems, like cameras that use lenses with visible light, X-rays are much more primitive. The basic idea is that we take photographic film, which is sensitive to light, we place that in a sealed pouch so it can't be exposed by the visible light around us, and then we place that behind the part of our body that we want to X-ray. And when that film is exposed, we're essentially seeing a shadow of our internal body that's cast by the X-ray light that passes through our body. So much simpler than the camera. Now you might know that photographic film is actually made of white silver oxide crystals. And the reason these are used is because they're photosensitive, which means that they will turn from white to black when exposed to light. Now, as X-rays pass through our body, some parts of our body will actually absorb all or a significant portion of those X-rays, and they won't therefore pass through to the other side. Now, this property of absorbing X-rays is referred to as attenuation, and we say that that part of the body attenuates X-rays. Now, since no X-ray light will pass through that part of the body, that means that the film behind that part of the body will be unexposed and will remain white. However, in other areas where the X-rays do pass through the body, they'll strike the film and then they'll expose it and turn it black. So the parts that X-rays don't pass through remain white, the parts that X-rays do pass through turn black. Now, exactly what your X-ray image looks like when you develop it depends on three factors of the X-rays that you're using for that particular application. And they are the attenuation of the X-rays as they pass through the objects, in other words, how much of the X-ray beam is absorbed, the penetrating power of the X-rays, which we'll come back to, and the exposure time, which is how long the X-rays are actually directed at the body. Now, so you can see in this diagram here, just an X-ray image of a hand holding a little metal model of the Eiffel Tower, and you can see that there are different attenuation for different parts of the body. So you can see that the bone has partial attenuation, so absorbs some of the X-rays, but allows some of them to pass through, whereas the soft tissue surrounding the X-ray, surrounding the bone, absorbs or attenuates very few X-rays, and most of them pass through. So you can see that the soft tissue part is mostly black. Now, the Eiffel Tower itself, which is made out of metal, essentially attenuates all of the X-rays. You can see that the area behind that on the film is extremely white, which means that almost all of the X-rays that hit that metal model will absorb, and very few pass through to the other side. Which leads us on to our next point. What determines how much or how many X-rays are attenuated by a particular material? Well, there's three things. Firstly, there's the density of the material. So denser parts of the body, like bone, tend to absorb or attenuate more X-rays than less dense parts. When we say less dense, we're generally talking about soft tissue. Soft tissue is a term which describes muscles, skin, internal organs, that kind of stuff. So they're not as dense as bone is, so therefore they do not attenuate X-rays to anywhere near the same degree. Now, if you think about that little metal Eiffel Tower, that's significantly more dense than bone, so that will have even greater attenuation. And that's one of the reasons we see that Eiffel Tower is coming up as being so white on that X-ray image. So density makes a difference. The second factor that affects attenuation is the thickness of the material. So the thicker the material is, the further X-rays have to travel through it, and therefore the greater the likelihood of an X-ray photon being absorbed by the material. So this means that if you have two parts of the body which have similar density but different thicknesses, the thicker part will absorb more X-rays. So for example, your lower arm and your upper thigh are the same thing basically, soft tissue with a bone in the middle, but an X-ray of the upper thigh will show much greater attenuation than the lower arm will, because your upper thigh is much, much, much thicker than your lower arm is. And the last factor, and perhaps the most complicated one, is what we call the effective atomic number of the material. Now, for reasons that we don't have to go into at stage 2, materials that have higher atomic numbers will tend to be better at absorbing X-rays. So that's another reason why that metal Eiffel Tower in that X-ray image showed up much clearer, showed up much whiter in the image. The metal, I don't know what kind of metal it was, but the metals generally have higher atomic numbers than the kinds of elements you find making up organic matter. So our body is mainly low atomic number elements like carbon, hydrogen, and oxygen, whereas metals are much further down on the periodic table and have much higher atomic numbers, and therefore will tend to attenuate X-rays to a much greater degree. Now it gets a little bit complicated here, because most of the organic materials in our body are not pure elements. So they're actually made up of two or more different materials. So for our body it's mainly carbon and hydrogen, but there are certain amounts of other elements in there as well. So when we talk about attenuation from material and how it's affected by atomic number, we generally talk about the effective atomic number of a material, which is kind of like a weighted average based on all of the different elements that make up that material and their atomic numbers, and the proportion to which they appear in that material. So for example, if you're dealing with soft tissue, you would find the effective atomic number would be weighted more towards carbon than other elements, because carbon makes up the greatest proportion of organic matter, or of the elements that makes up the organic matter in our body. Okay, so the last factor is the effective atomic number. The higher the effective atomic number for a particular material, the more likely X-rays are to be attenuated as they pass through that material. Okay, so attenuation is one factor to consider. The next factor to consider when making an X-ray is the penetrating power of your X-ray. Now, X-ray photons that carry more energy will penetrate further into your body before they're absorbed. So we say that the penetrating power, which is also sometimes referred to as the hardness of an X-ray beam, increases as the photon energy of the X-ray beam increases also. Now we saw in the first video that in an X-ray tube, using higher voltages will give you electrons that are traveling with greater kinetic energy when they strike the target metal in the X-ray tube, and therefore that will produce X-ray photons, which also carry greater energy. So we can adjust the penetrating power or hardness of an X-ray beam by adjusting the voltage we use in the X-ray tube. If we want harder X-rays, we use higher voltages. If we want softer X-rays, we use lower voltages. So as a rough guide, hard X-rays, typically you'd have tube voltages of anywhere between 100 and 150 kilovolts, whereas if you're using soft X-rays, you might use a tube voltage of anywhere down to maybe 50 kilovolts instead. Now, whether you're using hard or soft X-rays, it depends on the application. But if you were trying to look at a bone, like you're trying to see a break within a bone, then you'd probably use hard X-rays for that, because you don't want to see the soft tissue surrounding the bone. That would just obscure the image. You just want to see the bone itself. So if you use hard X-rays, those hard X-rays will tend to pass almost unimpeded through the soft tissue and will only be attenuated to any degree by the bones. So that will make the bone stand out amongst the soft tissue. On the other hand, if you were trying to use the X-rays to look at soft tissue itself, then you would use much softer X-rays so that they are absorbed by the soft tissue, and rather than just passing straight through it like a hard X-ray beam would. So in this picture here on the right, we're looking at tumours within a patient's lungs. So we want to use soft X-rays so that the tumours, which are soft but of higher density or thicker thicker essentially than regular lung tissue, stands out against the regular lung tissue. If we used hard X-rays, those hard X-rays would pass straight through both the soft lung tissue and the tumours within that person's lungs. Soft X-rays are sometimes also used if the thickness of the material that the X-rays have to pass through is quite thin. So for example, if you're getting dental X-rays, even though you're dealing with teeth, which are fairly dense, I suppose, the X-rays themselves only have to penetrate a very small distance from one side of the tooth to the other. So dentists generally tend to use quite low tube voltages, like 60 kilovolts, which produces soft X-rays. And the last factor we need to consider when tuning an X-ray is the exposure time. Now, these days we generally use short exposure times when we take X-rays. That first image at the beginning of this PowerPoint, which looked at Röntgen's image of his wife's hand in 1895, I believe it took about 15 minutes to take that X-ray, which is quite a long period of time, whereas modern X-rays generally just a couple of milliseconds. Now, there are two reasons why we want to use short exposure times. Firstly, we know that X-rays are ionizing radiation, which means that they pass through our body, they knock electrons out of the atoms that make up the molecules in our body, and this changes their property. It ionizes them and causes them to react chemically in different ways, which can lead to cell death, it can lead to cancers, mutations, that kind of stuff. Very undesirable. So what we want to do to minimize the likelihood of damage to our body by ionizing radiation is to expose patients to this X-ray radiation for as short a time as possible. Now, second reason we use a short exposure time is just like when you take a long exposure time picture with a camera, if you use too long an exposure time with X-rays, there's a likelihood that the patient, who is generally conscious when you take an X-ray, is going to move, and in doing so they'll blur the image that you see when you look at the X-ray later on. So to stop that from happening, you use a short exposure time. It's less likely that the patient will move while you're taking the X-ray. So usually we use a short exposure time, as I said before, a couple of milliseconds, and to compensate for that we normally use a fairly intense source of X-rays. So, you know, intensely means how many photons per second. It doesn't mean how hard the photons are or how much energy they carry. So if we want more X-ray photons per second, a more intense X-ray source, then we need to have more electrons striking the target metal, which means that we increase the current through the filament. So we keep the tube voltage the same, but we increase the current through the filament to release more electrons, which produces more X-ray photons when the electrons strike the target. So by doing this, short time, high intensity exposure, that produces better X-ray images. Okay, so that finishes this video. The last video in this series will finish off this topic on wave-particle duality by looking at things called matter waves and the work of a physicist called Louis de Broglie. Okay, thank you for your time.